All right, this is going to be a surface integral of a vector field. Our previous examples were all surface integrals where the thing we were integrating was a scalar function. Now we're integrating a vector function, a vector field. And these vector surface integrals are called flux integrals. The surface we're going to integrate on is the upper half of a sphere of radius 1. So that we start with the same kind of process. We need the parametrization for our surface, and the parametrization for a sphere is going to be the radius, which is 1, times cosine theta sine phi, and cosine phi. So those are the x, y, and z coordinates that we'll be dealing with on our surface. We need the normal vector, and we've already found that the normal vector is r squared, which in this case again is just 1 times cosine theta sine squared phi, sine theta sine squared phi, cosine phi sine phi. So there's our normal vector. And I guess with the parametrization, we should have been more careful and included the parameter domain. So the domain here, we have the entire upper hemisphere of the sphere. So theta is going all the way around, so 360 degrees. But phi is just going to pi halves, because it's just from the upper the z-axis down to the xy plane. So that's our parameter domain. Those are going to become the endpoints of integration for us. Let's put theta on the outside, phi on the inside. And what we want to do is take our function that we're integrating and rewrite that in terms of our parameters. So that's z comma x comma 1. So z on our surface is cosine phi, and x is cosine theta sine phi, cosine theta sine phi, and 1 is 1. So that is z, x, and 1, which is the function we're integrating, z, x, 1. So on the surface, we use the value of those things on the surface using the parametrization. For a flux integral, it's not the normal vector, the magnitude of the normal anymore. It's the dot product with the normal. So it's the dot product of that with our normal vector. And then we're going to have our d phi, d theta. So we have to compute this dot product. That's cosine phi times cosine theta times cosine phi times sine squared of phi, plus the y components, cosine theta sine cubed of phi, plus the third component, cosine phi sine phi of a d phi d theta. I've often been taking the 2 pi out for the theta integral. I can't do that because we do have theta dependence now. So we're going to have to do both of the integrals and see how to do them both. At this point, it really is just Calc 2 integration techniques. That doesn't mean necessarily that it's easy, but that's all it is at this point, is a bunch of Calc 2 integration. And for the first one here, we would use the fact that sine squared phi is 1/2 minus 1/2 cosine 2 phi. Then we can integrate that. For the third bit here, we'd use a u substitution. U equals cosine phi, so du equals negative sine phi d phi. We could actually let u equal sine phi the other way around. Either way, we'll get the same answer. And for this last one here, sine cubed of phi, we're going to break that up. Sine cubed of phi is sine phi times sine squared phi, which is sine phi times 1 minus cosine squared phi. And then we can let u equal cosine phi with du equals negative sine phi d phi. We do all of that, do all of the integration. We still have some theta integrals to do. The theta integrals are also going to involve u substitution on the second one, not on the first one. So lots of integration to do once we reach this point. Not necessarily easy integration, but it's all stuff that we can do and things that we've learned how to do. I wanted to show you how to set it up. This is the flux integral, and the answer we get is called the flux. And what's involved is the parameterization and the normal, and then the dot product of the two, and that's what we integrate.